Welcome to Semantic Web Technologies, Lecture 1, the Web of Data, Part 6, the Vision of the Semantic Web, Part 2. In the last part, I have introduced to you the vision of the semantic web and what does it mean to explicitly represent knowledge within the web and what to do with that knowledge. Now, we want to take a closer look at the technology that is behind the semantic web. So we have already learned about that semantic web technology stack, and now we want to take a closer look into the single layers and what is it all about. So what we do now is I will give you short examples, for example, how things can be identified on the web, how knowledge and facts can be expressed, and how models that lay behind or above this represented facts can also be explicitly represented within the web and with the languages that are defined in the semantic web technology stack. So this will only be first examples. So you get a glimpse about what the semantic web means. We will go in detail on all these technologies in the course of this lecture. Okay, so let's start with the basic layer. The basic layer and the foundation of the semantic web, of course, is the World Wide Web. So we rely on all the technology that is in the World Wide Web. First thing is, of course, we have to identify things we are talking about and that we want to represent knowledge about. And therefore, we apply an already existing addressing and identification mechanism that the web provides. And this, of course, is the URI, the Uniform Resource Identifier. And when we come back to the example from the last part, where we had Fabio Capello, who was the the soccer manager of the UK national team. For example, we can give a URI identifying this person, identifying Fabio Capello. And here you see the URI. It is based on the so-called DBpedia, which is the semantic version of the popular known Wikipedia encyclopedia. And of course, in the Wikipedia, there is a wiki page about Fabio Capello, the soccer manager. And then, of course, we can, as an identifier, take the URI of the page in the Wikipedia that describes Fabio Capello. But we are in the semantic web, not in the real web, so we do not take the URI from the Wikipedia, but from the semantic version of the DBpedia, where all the knowledge of the Wikipedia is expressed in a semantic way that it can be accessed by machines and understood by machines. So, for example, here Fabio Capello, we have here the Wikipedia page of Fabio Capello. And how to extract semantic knowledge that is implicitly hidden in the Wikipedia and how to create the DBpedia from that. That's pretty simple. For example, you maybe have noticed that in the Wikipedia, many pages are created in the same way. It means there is a template for certain classes, for example, for persons, like for Fabio Capello. And in the template, you have a little box and a little table on the right side where, for example, there's the place for a photograph or a picture of that person, and where there's a small table where always the same information is provided. For example, the full name, the date of birth, the birthplace, and other details about this person. And because this table also is a template, this information here is somehow structured information. And it's pretty simple to extract this structured information and to connect, of course, the single part of the structured informations with according knowledge representations that give us a clue about the meaning of these properties. And this then forms the so-called DBpedia, the semantic version of the Wikipedia. In the DBpedia, when you look at the same page denoting Fabio Capello, you will find a lot of facts about Fabio Capello, and all these facts are expressed with the help of a language that can be read by machines. And this language is called RDF. It's the Resource Description Framework. And here we are on the blue layer for the information exchange, where we really can express knowledge in the form that we can state facts and we can communicate about these facts. To represent a fact is pretty simple. It's somehow in RDF like in pretty simple sentences in our natural language. Because every bit of knowledge, every fact in RDF consists out of a subject, what we are talking about, out of a property, which means the subject has a specific property, and an object, which means the property has a specific value. So subject, property, object form simple facts in RDF. And this is pretty straightforward to read. For example, if you say Fabio Capello is of type or belongs to the class soccer manager. You see here the soccer manager. This is also a URI. It's a short form because we have here used a so-called name prefix, which is, if you expand it, the URI of the DBpedia, for example. And also here the 2 points also denote, in this sense, a shortcut for a URI. But we will talk about that when we come back to RDF in detail. So here, for example, you have a few facts that you can gather from DBpedia about Fabio Castello. For example, that he has the birthplace San Cancian, that he has a birth date, and that he is a soccer manager. Whoops, we have to go one step back. That he is a soccer manager, and that, of course, he is also a person. The next step would be we need models of our world that tell us what is a soccer manager, what is a person. And this can be done one layer above with RDFS or OWL. In RDFS, for example, you can tell or state what a soccer manager really is. And you do this in the same way. You build up the model also in tiny little sentences in these facts consisting out of subject, property, and object. So RDFS and OWL can be represented as RDF, as small triple facts. So for example, here the soccer manager is a class. And of course, the soccer manager is a subclass or is part of person. The soccer manager is a person means that. And I can give this class a name, in this sense, a label, soccer manager. And I can say, for example, birthplace, it's a property. And it's a property that every person has. So the domain of this property is person. And of course, birthplace means that a person has a place as a birthplace, so place will be the range of the property birthplace. On the other hand, birth date also is a property that gives a person some date when the person is born. So the property birthplace and birth date are two properties that assign to a person new characteristics concerning, for example, where the person is born and when the person is born. So this is the way how knowledge is represented on the web. And the machine can read this. And of course, it can then deduce when a fact is given, for example, that Fabio Capello is born in San Cancian, and we have a birthplace that we say Fabio Capello has birthplace San Cancian. Then, of course, we can deduce from that fact that San Cancian must be a place, because in the ontology here, we have the statement that birthplace is a place. So that's pretty simple. So you see here, you can represent these facts also in a graph representation. So you have here the soccer manager, it's a subclass of person, and a person has a birth date and a birthplace. So this is only a kind of other representation. This is not machine readable, and this is pretty simple machine readable. But we know more about, let's say, for example, soccer manager or persons, than only that a soccer manager is a person or that a person has the birthplace. So there's much more complicated knowledge that has to be expressed. And one way to do that is with ontologies based on the OWL ontology language. the web ontology language. So for example, I can say, for example, that Fabio Capello is also part of the class or belongs to the class of living people. And to distinguish living people and already dead people, I have to make a statement, for example, that nobody or no individual can belong to both classes at the same time, to the class of living people and to the class of dead people. So I can express this fact with the help of logic that I say these two classes are disjunct. It means no individual can be at the same time part of both classes. So this would be a logical constraint. And this kind of logical constraint can only be then represented one step higher here, for example, with the help of the OWL web ontology language, or much more complicated facts then can be represented with the help of rules. For example, you have here an interesting rule, for example, and this rule is expressed in description logics, and it only says that all persons that have a death date must be dead, of course. But we will come back to that later. You will see that also to express knowledge with the help of logic or description logics is pretty simple when you get used to the syntax and when you know about the semantics and how to use that. So only to give you a first clue about how knowledge is represented in the semantic web. And then, of course, if I can represent knowledge, I also must access knowledge and to query knowledge. And I can do this, for example, with the help of a specialized query language. In the semantic web, it's the Sparkle query language. And with that query language, I can formulate simple queries. For example, I can look up all soccer players that have scored more than 10 goals as members of a national team. Now you might think, okay, this looks like a pretty complicated query, but as computer scientists, for example, you might be familiar with the database query language SQL, and Sparkle is pretty much like SQL. You see here the same keywords, for example, select from where. But in the end, the processing is a little bit different because all these facts, they represent large graphs, and therefore this Sparkle language is something like a graph access language and is based on graphs, and it tries to extract subgraphs that match all the conditions that have been stated in the query. So when you, for example, now process this query with a Sparkle processor, you will receive an answer, and then you will get a list of all soccer players that have scored more than 10 goals as member of a national team. But if you look closer on that list of answers that has been generated from the DBpedia, you will immediately, for example, see that, okay, one of the top scoring soccer players plays in the Denmark national handball team, and handball, of course, is not soccer. So here we have a problem because, of course, I can play soccer, and on the other hand, I can simultaneously also play handball. And for example, I might be in the national team of handball while I'm only in the amateur league of soccer. And then, of course, this question must be formulated much more stricter. So we have a problem with the data quality on the one hand in the DBpedia and Wikipedia. There we have data quality problems because Wikipedia, of course, does not rely on a strict formal reviewing process by experts, and every user can contribute information. So there are, of course, inconsistencies and failures and errors. And on the other hand, of course, I have to be careful when I really formulate my question, that everything that is implicitly somehow in my mind when I pose this question must be made explicitly to get the right answer. So this is a big problem. Okay, so this is a first clue about what is possible in the semantic web and what is the technology behind there. And as a next step, in the next part, the last part of the lecture, we want to take a short look on a few applications in the semantic web and in the web of data.